There's two more things that I want to talk about with the amine or nitrogen nucleophiles. The first thing that I want to talk about is reversing the reaction. I showed you with the primary amines, I showed you an example of how the reaction is reversible. I didn't do that with the secondary amines, but it is also reversible in just the same way. And so we're going to draw this. This is called retrosynthesis, backwards synthesis. Of the imine and enamine. What I'm going to do is use the product from the imine synthesis, and we're going to retrosynthesize that guy. So that he looked like this. That was our imine. When we do this retrosynthesis, the retrosynthesis is also acid catalyzed. In this one, it's a dilute acid. So sometimes you're going to see water listed as one of the reactants, but the water may not be written down. May not be written. Might be left off completely, or it might just say dilute acid. So if you have to come up with the products of the retrosynthesis, and a question for this would be something along the lines of, give the structure of the amine and the aldehyde that were used to make this particular imine. What do they look like? So if you have to answer a question like this, you can draw the mechanism backwards. So you could go up here and you could start here at the end, and then you could just backtrack your way all the way through the mechanism, all the way back to the beginning. That's definitely possible. It is kind of tedious, and you know that I really like mechanisms, and I don't like to promote just memorization of things. I like you to understand why things happen. But this is one of those reactions where I almost feel like it's easier if you don't learn the mechanism and instead learn a shortcut. So I'm going to show you the shortcut. When you're asked to come up with the carbonyl compound, the aldehyde or ketone, as well as the nitrogen that forms an imine, I want you to visualize slicing the molecule in half at the carbon-nitrogen double bond. I'm going to draw that, and I'm going to draw little stubby bonds where I sliced it. So I've sliced the molecule in half at the carbon-nitrogen double bond. And to these fragments, these two pieces, I am going to add the water that is being added in this reaction. And I'm going to do that by adding an oxygen to one of these two pieces, and I'm going to add 2 hydrogens to the other piece. Remember that we are going back to an aldehyde and amine. So we need to make an aldehyde, which means we've got to put an oxygen on that carbon to something double bond. It's got to be there because we have to make an aldehyde. So there's one of our products. The 2 hydrogens are going to go over here on the nitrogen, but not like this. That's not an option. So instead of the nitrogen having a double bond, now it just has 2 single bonds to 2 hydrogens. So those are the 2 products of this retrosynthesis reaction. I've got them kind of jammed up together. And if you look back in your notes to this particular reaction that we did forward, you'll see that these are the aldehyde and the amine that we used to synthesize the imine. For the enamine, we're going to use the same enamine that we did here. For the enamine is a little bit trickier. Let me redraw this guy. When you're doing the retrosynthesis of the enamine, the conditions are exactly the same. You need to have acid catalyst, and there is water in this reaction, although the water is not always going to be written down. And so your trick in this case, the first thing that you need to do is make the enamine look like an imine. So what I'm going to do, I'm going to go down here on the side and I'm going to rewrite it. And I'm going to move the carbon-carbon double bond to make it a carbon-nitrogen double bond, because my goal is to make this look like an imine. And that's not a invalid move, because if you remember back in the mechanism, that is a thing. Like, that happens in the mechanism. So we've just backed it up one step. And backing it up to this step is going to make it easier for us to make some predictions. So now we can treat it the same way that we treated the imine. We're going to slice it at the carbon-nitrogen double bond, and let's separate those two parts. And I'm going to leave the little stubby bonds on there. Like that. And we are adding H and H and O. The oxygen is going to go here, just like it did with the one above, because we know we have to make an aldehyde. The H's, are you going to cram both of them right here? No. Because that's not what we started with. We don't start with a weird nitrogen that has 4 bonds on it. So where does that second hydrogen go? Because one of them is definitely going on there. Where does the second hydrogen go? If you remember back to the mechanism, in order for us to move, when we were going forward, in order for us to move from this guy right here to the enamine, we pulled off a hydrogen from one of the carbons. So the second hydrogen, when we're adding a second hydrogen in this reaction, it's actually going down here, which is probably kind of confusing to remember, but that is where it ends up. And in this trick, when we move that double bond around, so in this part right here, when we redid the rewriting, when we moved the carbon-carbon double bond up to become the carbon nitrogen double bond, there were only 2 hydrogens on that carbon to begin with, which means there were only 2 hydrogens down here to begin with, which means that we did need to add this little guy right there. So these are the 2 products of the retrosynthesis. The last reaction that I want to show you in this section is called the Wolff-Kischner Reduction. And this is an extension of adding a nitrogen nucleophile to a carbonyl compound. This reaction uses one of our primary amine derivatives as the nucleophile. So let's slide back up and take a look here. When we're doing this reaction with primary amines, this is one of the options that we have as a primary amine to do the nucleophile. So if we're using that one specifically, and there's no substitutions here, you must use this one. First thing that we're going to make is just the imine that you would expect to make. And that guy can be further reacted with hydroxide, dilute with a little bit of heat, and watch this magic. Gone. Isn't that cool? This is a great way of removing functionality from a molecule. There's not a lot of situations where we want to remove functionality, because I know a lot of times I say we have to put something, we have to create functionality. We've got to put a functional group on this molecule so that it can do something. But maybe at the very end of a reaction, when you were all the way done with a synthesis and you've got this extra carbonyl group on there that you don't want to have on there, this would be a great way for you to get rid of it. It just slices it off like it was never even there.